Okay, let's just jump right into this. Welcome to this explainer, where we are tackling a really fascinating and frankly kind of terrifying engineering mystery. We're going to look at the microscopic villains that literally tear solid metal apart and the brilliantly simple yet ingenious techniques we use to fight back. We're talking about metal fatigue. You look at a massive steel bridge or a heavy-duty machine and it looks completely indestructible. But beneath the surface, there is an invisible war constantly raging. Sounds dramatic, right? But it really is. Today, we're going to decode the exact mechanics of why metals fail, and more importantly, how engineering science armors them against complete destruction. So the absolutely crucial point we need to address is this. Why does solid metal suddenly snap under pressure? I mean, we've all seen it or heard about it. A thick bolt just shears off, or a massive shaft breaks in half, seemingly out of absolutely nowhere. But the truth is, metal rarely fails all at once from a single massive blow. It gets exhausted. Think about bending a paperclip back and forth over and over until it finally snaps. Metals experience that exact same repeated cyclical stress, tension, compression, bending, and this cyclical stress starts a completely invisible chain reaction that quietly builds up over time. Section 1. The anatomy of metal fatigue, the Micro-Saboteur. What's truly staggering here is the scale. We are looking at the angstrom level. We're talking smaller than nanometers. When a piece of metal is subjected to that repeated stress we just talked about, the atoms on the outer edges actually start to shift. So step 1 is that cyclical loading. Step 2 is where the real damage begins. Because of the stress, localized groups of atoms either push outward, creating what we call extrusions, or they cave inward, creating intrusions. Basically, imagine the surface getting these tiny microscopic wrinkles. An intrusion is essentially a microscopic surface wound, and eventually, step 3 kicks in. That tiny little intrusion becomes the birthplace of a microscopic crack. As the machine just keeps running, that crack zips through the metal until snap. And this brings us to the absolute golden rule of metal fatigue. The beginning is the surface. Seriously, almost every single fatigue failure in the history of engineering starts right at the exterior boundary of the material. Why? Because that is where the bending stress is at its absolute highest, and that's exactly where those extrusions and intrusions form. What this tells us as engineers is profound. It means if we want to stop metal fatigue, our absolute first line of defense, without question, must be controlling the hardness and the integrity of the surface. Section 2. Crystal Combat. Ferrite versus Austenite. This atomic battle basically dictates why some metals fail incredibly fast. Take a crystal structure like austenite, for example. It has a lattice structure that is fundamentally spacious. Think of it kind of like a big empty room. When repeated stress pushes on the atoms, there is plenty of empty space for those atoms to just slide right into. And because they can slide so easily, the metal is relatively soft, meaning those dangerous surface intrusions we talked about, they form very quickly. But then you have a structure like ferrite. Ferrite has a densely packed core. There is literally an atom sitting dead in the center of its structural unit, just blocking the way. So when stress tries to push ferrite's atoms around, that core atom acts like a total roadblock. It offers high resistance, meaning it's so much harder for the surface to deform and crack. So wrapping up the material science side of things, the key takeaways are crystal clear. Number 1, surface hardness is what prevents those initial microscopic extrusions. Number 2, crystal structures with high internal resistance, like ferrite, are inherently better at fighting fatigue than the softer, more spacious structures like austenite. And number 3, specifically tempered structures like sorbite or trustite vastly outperform standard structures like pearlite. Why? Because they perfectly combine toughness with that absolutely crucial resistance to atomic sliding. Section 3. Solution 1. Armor through shot peening. Okay, let's really dive into this concept, because at first glance, it sounds completely counterintuitive. Shot peening involves literally bombarding the surface of a finished metal part with tiny, hard, spherical balls, often steel or ceramic shot. I know, it sounds like you're just aggressively vandalizing the metal, right? But you're actually creating a microscopic dent with every single impact. Millions of these tiny dents overlapping create a highly hardened, compacted shell around the part. We are essentially beating the surface into a state of permanent residual compressive stress. The basic physics of why that violent bombardment actually works is just fascinating. See, fatigue cracks require tensile stress to open up and grow. Tensile stress wants to pull the metal apart, but shot peening creates compressive stress on the surface. Compressive stress actively pushes the metal together. It acts like a tight physical corset wrapped right around the metal.
So when the machine operates and generates that dangerous tensile stress, that pulling stress first has to fight through the protective compressive armor we just installed. It effectively neutralizes the pulling forces.
And the real-world results? They're staggering. When we look at an SN curve, which is just a way to chart the magnitude of stress against the number of cycles a metal can survive, the data speaks for itself. A standard machined part without any peening treatment might survive a few thousand cycles before a crack forms. But by simply shot peening that exact same surface, the fatigue life curve shifts massively upward. The part can suddenly endure exponentially more cycles simply because those initial surface cracks are entirely blocked from ever opening up in the first place.
Solution 2, evasion through notch management.
Think about a simple accidental scratch, a purposely machined groove, or a sharp angle on a metal shaft. In engineering, we call these notches. And in the world of metal fatigue, a notch is basically a death sentence. Any surface irregularity acts like a ridiculously powerful magnet for stress. Instead of the physical load being distributed evenly across a nice smooth surface, all those forces funnel directly into the microscopic tip of that scratch. It's literally the absolute perfect incubator for a microscopic crack to begin.
Now let's look at how this builds mathematically. Engineers use what's called the stress concentration factor, which is represented by the Greek letter alpha. The formula is alpha equals 1 plus 2 times the square root of the depth of the notch divided by the radius of the notch. Now don't let the math scare you. The crucial point is actually right inside that square root. The only variables that determine how incredibly dangerous a scratch or a groove will be are how deep it is and the radius of its curve. That's it.
Okay, let's plug some real numbers into that formula just to see the impact. Imagine a sharp, deep cut. Let's say it has a depth of 10 and a tiny tip radius of just 10. The math spits out an alpha of around 3.2. That means the stress at the very bottom of that scratch is multiplying by more than 3 times. It's going to crack almost immediately. But if we take that exact same area and instead machine it into a shallow, smooth curve, say keep the depth at 10 but use a large radius of 100, our alpha drops all the way down to roughly 1.3. By simply increasing the radius, we disperse the force and drastically eliminate the danger.
So this translates into some incredibly strict, non-negotiable rules for machinists and engineers. Bullet 1, you absolutely must avoid sharp 90-degree angles anywhere on a moving structural part. Bullet 2, surfaces have to be polished to remove even accidental tooling scratches because, as we've learned, a scratch is just an unintentional notch. And bullet 3, wherever a groove or a step down in a shaft is actually required for the design to function, that transition must be machined with the maximum possible radius. Simply put, smooth curves save lives. So we've gone all the way from the microscopic shifting of atoms inside crystal structures to the high-impact armor of shot peening, right down to the elegant mathematics of rounding out a sharp edge. The next time you're driving over a massive suspension bridge, flying in a commercial plane, or honestly just looking at the engine block of your car, take a second to think about the invisible war happening right on the surface of that metal. I'm going to leave you with this thought to ponder today. Look at the heavy machinery operating all around you. Which of these invisible, microscopic structural defenses is working overtime right now just to keep it from snapping in half? Thanks so much for joining me for this explainer, and definitely keep questioning the mechanics of the world around you.